Hello everyone, my name is Mostafa Alani. I'm a faculty member at the College of Engineering at Al Araqiya University. Today I am going to present our paper, Beyond Flat Surfaces, Parametric Derivation of Historical Islamic Geometric Designs, which has been done in collaboration with my co-author, Dr. Sama Al-Aggam, a faculty member at Istanbul Technical University. Patterns are a common feature of Islamic architecture that exist in a variety of shapes and types. In general, Islamic patterns have been classified into two main categories: Arabic calligraphy, in which various types of calligraphy used for architectural decoration, and the arabesque, which also can be further subdivided into two subcategories: floral and geometric patterns. Today's presentation concerned with the latter, the geometric patterns. Geometric patterns consist of a repeated unit and a repetitive structure. The repeated unit is the minimal possible region that contains the basic geometrical composition, where the repetitive structure is a product of systematically replicating the repeated unit to fill the space completely while leaving no gaps. Historical Islamic art and architecture took advantage from the mathematics of its age, the enormous diversity of complex form that exists in Islamic art and architecture are products of mathematical and geometrical advancements as discussed in the available historical documents. One such document is رسالة فيما يحتاجه الصناع من أعمال الهندسة on the geometric construction necessary for artisans by Abu Wafa al-Buzjani, which shows that mathematicians collaborated with artisans to explore new relationships and perfect designs. The vast majority of IGB found on flat surfaces. However, some geometric designs were found on non-flat surfaces, such as the geometries found on some Mamluks domes in Egypt. Those compositions show the different levels of proficiency with some unique geometrical constructions. The recently completed Cambridge Mosque shows another example of the creative use of geometry in Islamic architecture. The ceiling design of the mosque is based on Islamic geometric patterns, yet the constructional component of the free-form wood ceiling morphed in certain places, forming the columns. Another interesting example that shows the creative employment of Islamic geometric patterns is the Louvre Abu Dhabi, which also features geometric patterns that are placed on the top of the dome. Although these two projects employed Islamic geometric designs on non-flat surfaces, still these two projects show two different approaches to deriving three-dimensional forms. Both approaches can be traced back to historical precedents. As mentioned earlier, historically Islamic geometric designs exist beyond flat surfaces. For instance, the muqarnas, which is a vaulting decorative component, shows some of the earliest attempts to employ Islamic geometric designs to generate three-dimensional compositions, where two-dimensional design blueprints were used to guide creating three-dimensional forms, as shown in the Topkapi and the Tashkent scrolls. Carbandi is another possible employment of geometric designs to derive forms beyond flat surfaces, such as the ribbed dome that exists at the Great Mosque of Cordoba. Unlike muqarnas, the geometry is curved as it's being projected into a round surface. The dome of the Karatai Madrasa features the geometric patterns that were morphed to cover the dome's interior. Another remarkable example that exists in Cairo at the dome of Sultan Qutb complex. The dome is covered with several star patterns that were designed to fit the dome. This quick overview of historical and contemporary precedents aims to develop an understanding of the variety of existing non-flat geometric designs by which two-dimensional geometric designs were employed to derive forms beyond flat surfaces. Generally, Islamic geometric designs consist of series of points connected to form a line or a polyline and then replicated using symmetry to fill a specified space. Typically, Islamic geometric designs show some or all of the following recognizable characteristics: symmetry, flow, unboundness, and interlacing. Islamic geometric designs morphologically relate to each other, and it is possible to morph a design to transform it from one state into the other. Three types of symmetry structures were identified in Islamic geometric designs: rosettes, periodic, and quasi-periodic structures. The figure shown in this slide shows an example of 3 points that were connected with each other using a single polyline and experimented with to create designs using these 3 structural orders. This paper presents 2 methods by which Islamic geometric designs can be employed to derive 3-dimensional compositions. These 2 methods are Euclidean point extrusion and curved surfaces fitting. Regarding Euclidean point extrusion method derives 3-dimensional composition from 2-dimensional Islamic geometric designs by manipulating the point's z-coordinate with no changes to the x and y coordinates. Muqarnas is an exemplar case of the Euclidean point extrusion method. Now, the challenge in deriving the forms in this method lies primarily in filling the gaps that may result with appropriate form, hence the curves you see in this figure. The curved surfaces fitting method aims to fit a 2-dimensional Islamic geometric design into various non-flat surfaces. It can be further categorized into 2 subcategories: curve directional projection and curve mapping. Both subcategories require a hosting surface to project or map the design to. Similar to the Euclidean point extrusion method, the curve projection method also extrudes points in the z-coordinate with no changes to the x and y coordinates. However, the value of the z-coordinates is determined by the hosting surface. Additionally, the curves that connect design points are generated by solving the intersection of the extruded design with the hosting surface. Thus, the curves inherit the hosting surface curvature while conducting no changes to the x and y coordinates. Depending on the design problem, the curve projection method could be limiting. Consider the hemisphere shown in this slide, which shows an Islamic geometric design projected into a dome-like hosting surface. This figure clearly shows that the design is strongly distorted at the bottom boundary of the hosting surface. This limitation is addressed by the curve mapping method. The curve mapping method would conduct significant changes to the x, y, and z coordinates of the design points and changes to the respective curves. That is, the points will be relocated into a position that is relative to the original position in the 2-dimensional design. In all of the explored scenarios, the 2-dimensional Islamic geometric designs played a foundational role in creating the designs beyond flat surfaces. Therefore, designer's sensibility is crucial as it will affect outcomes significantly. The Euclidean point extrusion method allows for an additional layer for designers to be creative in connecting designs parts and filling the gaps resulting from the extrusion process. In the curved surface fitting method, designer sensibility primarily resides at the 2-dimensional level and the hosting surface, and all changes need to be conducted there. Historically, Islamic architecture embedded a firm understanding of geometry that served functional and aesthetical purposes. Categorizing the corpus of existing designs and identifying generative processes of such designs is necessary to understand historical designs and provide a platform to progressively develop Islamic architecture. Consequently, the aim of this study is twofold. First, the paper aims to investigate Islamic geometric designs on and non-flat surfaces and categorize the different possible ways by which Islamic geometric designs can exist on non-flat surfaces. And secondly, the paper seeks to unveil computational processes by which such structures can be generated. visiting in the process uncharted territories to expand the search for novel forms. This concludes our presentation. Thank you very much for listening.